Hello, class. Mr. Bean here. Uh, this is video number 9, Pulleys and Tension for AP Physics 2020. These are lecture notes that I will present here on Kami, and then I will upload it to Google Classroom, so therefore you will have a copy of the notes as well, or you may want to take notes as we go along. So in this video, we'll be talking about pulleys and tension. So tension is a force usually associated with a string or rope. So let's take a look at an example over here. Here we have a block resting on a surface here. There's no friction. This time there's no friction. And look at the forces acting on this box here. There's tension being pulled in this direction, and usually T, we use tension for T, and mg is acting downward, and upward is the normal force. This N is normal force. All right, so let's go ahead and take a look at it and see what's going on here. So there it goes. It begins to move. It's accelerating here, and we'll hit pause. Okay, so at some time here, it looks like it reached a final velocity of 9.1 meters per second. So we want to take a look at this, and we want to figure out how do we get this acceleration here. Well, let's go over here and let's take a look at it. And I want to make sure I'm opened up here with Kami. Let's see. Here we go. Oh, there we go. All right, we're at Kami here. And so take a look at here. So here's our flat surface here. And here's our block here. And this block will have a mass, let's say mass of M. Okay. And there's a tension. Well, there's some force that's being applied here. It could be a push or a pull. And we want to identify the other forces acting on this box here. So we're going to, so we do have a normal force acting upward. And I'm going to write it this way. I'm going to write with a capital F with a subscript N to indicate normal force. Okay, and there's a force being in this direction. And there's also the force of mg. So we have forces acting in the y component, the y direction, and as well as the x direction. So for our frame of reference here, I'm going to go ahead and draw like a L here, and to show that this is positive and going up is positive, because we do have to consider both directions. So let's go ahead and analyze this. And so I'm going to go ahead and change colors here, and let me go to red. And I'm going to go ahead and talk about the system. So the system is everything that's inside the circle here. We do not care about anything acting outside the system here. Okay, and let's go back here. So we're going to do our analysis here, and let's take a look and see what we got. So we have some of the forces. Okay, now we talk about X or Y. Well, if you look at the Y direction here, this is going to be sliding in this direction. So there's no acceleration vertically. So so if I was to do some of the forces in the Y direction, and I would say that there's no acceleration up or down, that equals 0. So whenever some of the forces equals 0, I suggest doing this. All the forces going up equals all the forces going down, like so. So when I look at that, what's all the forces going up? Well, there's just one force going up. That is the normal force. And all the forces going down is just mg. So from an elevator problem last time, we have normal force equals mg. All right, so not too bad. So now let's consider the sum of the forces in the x direction. X direction. Okay, now it's not going to equal 0 because it's accelerating. See here, it's accelerating. So sum of the forces equals ma. Now I should, for precision, I should put an X here, but we'll just say sum of the forces in the X direction here. Okay, so the only force acting in the X direction is this force here. Now this force is probably going to be a string here, so we could say it's going to be tension. So the force is tension. So we'll go ahead and write a capital T here, tension. Now sometimes we'll use T for period, but for right now we'll just see T as tension. And that's going to equal M. Here we have AX. Okay, and so to solve for the acceleration, AX is just going to equal whatever the tension is divided by the mass. Okay, and that's how we solve it for just a simple case of just a string pulling a box like this. Okay. All right, so now let's take a look. Let's go the next level of difficulty. Let's consider we have two boxes now. So here's a box here, and we'll call this box here M1. It's attached to a string, and we will call this box here M2 as so. And let me hit pause. Okay, sorry about that, a phone ring. So here's M1 attached to a string here, attached to M2, and we do have some applied force here. So there's some force that's being applied here, and it is causing it to move along the x-axis here. And right now we have no friction. So I'm going to say no friction. So all of these examples, no friction. Okay, so we have no friction. Okay. And now M1 and M2 could be the same or they could be different. So we're not sure, but we'll just identify this as M1 and M2. Now there's a string here. Now this is applied force. Now it could be a string, but it's just a force being applied here. The tension is being applied right here. So there's a T tension that's applied right here. Now, what the tricky part here is, or not tricky, is what we have to understand is that there are two systems here. There's this system right here, which I will circle like so. There's that system. And then we have this system right here. Okay. So we have to consider only one at a time. We cannot do both at the same time. So let's consider system one here with mass one. Okay. And we'll go ahead and identify it as system one. Okay. So here we're going to assume, let's take a look at this point right here. Okay, there's a point right here. Okay. Now, since it's moving in the x direction, we'll ignore vertical. We'll say ignore. Hold on. We're going to ignore vertical motion. Ignore the y direction for right now. Okay, we'll look at that in a little bit. So system one here, we're going to look at this situation here. So we're going to assume that all the forces act on this point mass. And it could be the center of mass of this block here. Okay, we'll say the center mass of the block is right here. There's the center mass. Okay, so we have tension acting in this direction here with T. And I think that's the only force acting in the x direction. So here we'll go sum of the forces on system one is equal to M1A, like so. So the only force acting is tension. So we're going to put tension in here is equal to M1A, like so. Now we go over to system two here. Okay, so let's go and take a look at system two. Okay, so we're through with system one, looking at system two, and we're going to assume that all the forces are acting on this point mass right here in the center mass. So I'm going to go ahead and draw it right here, a free body diagram, and we have a force going this direction. Okay, there's a force here, and there's also tension. Now, it's the same string, so we don't need to identify it as T1 or T2. It's the same string, so it's tension going in this direction. So this way is positive. This way is negative, right, from up here. So when I do my sum of the forces on system 2 equals, now it's mass 2, A, like so. Okay, so what I have here is I have force, I have F here, minus tension equals M2A, like so. All right. Okay, so M2A. All right, so now here's what we do here. We now have two equations and two unknowns. So let's look at the left side and the right side of the equation. Let's look at the left side. Here's the key. The tensions must cancel out. So if I'm going to add the left side, this T here to over here, this is negative T, that's positive T, they cancel out, leaving just F on the left side. On the right side, I have M1A plus M2A. So we'll go ahead and write down here M1A plus M2A, like so. All right, so here's force here. Now I think I can factor out the mass, okay, or excuse me, factor out acceleration. And I have m1 plus m2, like so. There we go. Now, if I want to solve for acceleration, it's whatever the applied force is divided by the sum of m1 plus m2, like so, right, equals acceleration. And that's the acceleration of the system. Once I have this, I can apply any of the kinematic equations to determine distance traveled, time traveled, final velocity, initial velocity, and things of that nature. All right. So now we're going to go ahead and go look at 3 blocks. Okay. Suppose now we have, here we have, so we have your M1. There's M1 attached to a string here. And we'll call this here, was it M2, like so. And maybe now we have like a third block here. Okay. And we'll call this here M3. Okay. And there's a force that's being applied here. So we have 3 block system. Okay. All right. So in this system here, there's F here. Okay. Here's our frame of reference. This is positive, and this here is also positive, like so. All right. So now we have. So we're going to go ahead and now this time this is going to be T1. This is going to be T2 because they are different strings. Okay, so we're going to go ahead and take a look at this system right here. We'll look at this system here, and we'll also look at this system here. So there are 3 systems we need to look at separately. Okay, so here, as I look at this right here, only thing we have is we have a force going this direction, which is T1 in that direction. Okay, therefore, sum of the forces, right, on system 1 is equal to M1A, and that gives us T1 equals M1A, like so. All right. Now we're going to look at, kind of draw a little line here. System 2 now. So we have here T2. Okay, there should be T2 going in this direction, T1 going there. So we have here sum of the forces is equal to system 2. It's going to be M2, was it A right here, right? Okay. Now, here's my free body diagram. I have T2 acting in this direction, and I have T1 acting in that direction, like so. Okay, T1. All right. So we have here, it's going to be T2 minus T1 is equal to M2A. Okay, and that's as far as I can go. Now let's go to the third system here, this one here, and take a look here, do a free body diagram. Looks like we have an F going here, and I have a T2 going in that direction there, T2. All right, so we'll do our sum of the forces on system, this is going to be system 3 here. System 3, okay, is going to be, looks like, oh no, this should be mass 3. Mass 3. There we go. Sum of the forces on system 3 is equal to M3A. Okay, so because acceleration is the same for all these blocks. Okay, and so here we're going to have we have F here minus T2, like so, is equal to M3A. Okay, all right. So now let's look at the equation here. So let's look at the, here, draw our equation here. Let's look at the left side. Here's T1 minus T1. They cancel out. Here's T2 minus T2. They cancel out. So the only thing left is just F. Okay, and then we have the right side. We have M1A plus M2A plus M3A. Okay, so if I factor out the A and then divide by the quantity or the sum of M1, M2, and M3, what I get is, here's the acceleration, here's the force right here, and what I have here is in parentheses, I have now M1 plus m2 plus m3. So as you can see here, from what we've surmised from the acceleration, is that as I increase blocks, the acceleration should decrease because the force is constant. As I add more mass here, the denominator is becoming bigger, which making this ratio smaller. Therefore, acceleration is smaller. All right. Okay. So let's go ahead and kind of scroll down here, and let's take a look at this should be part two, not pat two, part two. Pulling a box on a horizontal surface at an angle. So here we have, let's reset this here. And this time I'm going to put theta, let's say, oh, no, we want the mass to be the same. Let's go ahead and make this theta, let's make it 30 degrees. Why not? 30 degrees. All right. So we're going to be pulling it at this angle here. Okay. All right. Now I'm going to look at, let's see what I can look at here. I don't have any force vectors. I do not. Okay. So I have this here. And now look at the tension in the y direction and tension in the x direction. Okay. Let's take a look at this. I'm going to go here. Okay, see the normal force, see how big it is here? Now watch what happens as I begin to increase the angle of tension. Okay, there's a Ty, now there's a Tx. Okay, so this tension now is broken up into vectors, the Tx and the Ty. Now look at, as Ty increases, the normal force also decreases. So remember, the normal force is like a scale reading, right? So if I'm pulling this at an angle, the scale reading begins to decrease. So the normal force acting on the block decreases because there's an extra Ty component here. All right, so what does that mean? So let's take a look at it here. Here we have our block here. And again, no friction. So we're going to have here no friction. Okay, we're going to do this all again, except we're going to have friction. Let me hit phone's ringing. All right, sorry about that. Phone was ringing. So no friction. So we have your no friction, okay, like so. And we'll go ahead and say this has a mass here. And no friction. And we're going to take a look here at our XY coordinate. The Y coordinate is going to be positive going up and positive going to the right. It's important to make sure we have this dialed in. So this time let's say there's a string is attached right here. And we're going to call this a force here. It's being applied. And at this time, it's at some angle. So with respect to the horizontal, we will call this here theta, like so. All right, so let's go ahead and identify all the forces that are acting. So we have the normal force acting in this direction here. There's the normal force. Okay. And we also have mg acting in this direction here. Now I'm going to go ahead and change colors so we get a different viewpoint. So here, this is a vector here. Now I have the x component here. We'll call this here fx. There's fx here. And I also have a y component here going up this way. And we will call this fy. fy. Okay, let me go back to black here. And so now, so Fy is equal to F, right, sine of theta. Okay, and Fx here is called F cosine of theta. We'll say cosine of theta. There we go. All right, so now this time we have to consider both x and y. So let's look at the y direction. We'll call it here y direction here. And let's see what we got. Now, this is going to be sliding in this direction, and we don't anticipate it moving up and down. So therefore, some of the forces, right, some of the forces in the y direction are going to equal 0. When it equals 0, I suggest going up equals down. All the forces going up equals all the forces going down. Therefore, we get rid of the negative signs. So we don't have to worry about negative signs. So what's all the forces going up? Well, we have clearly the normal force going up here. And also look carefully here. We also have Fy. Okay, this force right here, Fy. So I'll just go ahead and write Fy for right now. And what's going down? only forces going down is mg, like so. All right, so now let's take a look here and see what we got. There's Fn, right? It's just like the elevator problem, similar to the elevator problem. Plus here, Fy, we have this going to be F sine of theta equals mg. So the normal force, so let's take a look at the normal force here. Let's solve for the normal force. The normal force is going to be whatever mg is, right? Minus F sine of theta. F sine of theta. So because we're pulling it at an angle, there's this component here that's contributing to the normal force. So if there was a scale here, the normal force would read less. And intuitively, it should make sense here. Because of this y component, the normal force is less because there's a subtractive effect here. Okay. All right. So now that's in the y direction. Now this is accelerating in the x direction. So we'll go over here and we'll do x direction here, x direction, and we'll say sum of the forces in the x direction here is equal to ma, and we could write ax here to for the x direction. And so the only force acting here is the f, was it cosine theta, right? F cosine of theta is equal to max, like so. So the acceleration in the x direction is going to be the cosine component, cosine theta, divided by m. Okay, and that's should be consistent with what we had up here. Okay. All right, you guys. All right. So part 3, if you need to take a break, now's a good time to take a break here and stretch your legs a little bit. And before I start part 3. Okay, so part 3. Now we're talking about a pulley and what's called an Atwood's machine. So here's a pulley, and so right now we're going to ignore any friction, and we're going to assume that the pulley has no mass and the string here is massless. Okay, so we're going to assumptions. We're going to assume. Okay, so assume here the mass of the pulley is going to be 0. Okay, the no friction. Okay, no friction. Okay, this will come later. When we do rotational dynamics, no friction, and also what do I want to say? Mass of pulley is 0, no friction, and the string has no mass. Okay, string has no mass. Okay, all right. So pretty interesting. Okay, but in real life, these are real life situations we have to consider later on. All right, so here we go. And so here it is. There's some mass here, and let's go ahead and start it and see what happens. Okay, so it moved in this direction or accelerated in this direction, and it moved down. So here it shows us position, and here is velocity versus time graph. So if this is velocity versus time, that means the slope of this is the acceleration. Okay, so this will be a lab that we do in class, next class here. So let's take a look at this and let's figure out how do we calculate this theoretically. Okay, so let me go up here and let's go ahead and kind of draw a little pulley here. Here's a pulley. Okay, and we have some string right here. And we're going to call it has some mass, and this is a string here, and there's some tension acting in this direction here. There's tension right here. So this thing, when we release it, it falls in this direction, and it begins to spin in this way or rotate in this direction. So whichever way it rotates, we're going to take that to be the positive acceleration or positive direction. So it's going to accelerate in this direction, and we'll make it positive. All right, so when we do our analysis, I'm going to focus, here's our system right here. We're going to circle this, and we only care about what's happening inside the circle. In fact, we're going to assume that all the forces act on this point right here. So if I go over here and look at it, let's see what I have. So I have tension acting in this direction here, okay? And we also have mg acting in this direction. So looking at this here, hold on, let me make this a little bit. This is tension. There we go. Tension. So since it's accelerating in this direction or rotating in this direction, we'll make going down be positive and going up be negative in this case. Okay, so we do our sum of the forces. Okay, there's only one system here, is equal to ma, right? So here we have, so mg is going down plus tension acting, or hold on. It should be negative here. Let's get rid of this here. And we'll go here. Okay, mg minus tension is equal to ma, like so. So I want to solve, now here I can solve for tension or I can solve for acceleration. But let's say I want to solve for acceleration. In this case, I have mg minus tension divided by m, like so. And we'll put this in parentheses so we don't upset Aunt Sally. Okay, so there's the acceleration. And once I had the acceleration, I can easily solve for tension. Okay, so the next level is what we call the Atwood's machine. There's a link here for it. And this is an Atwood's machine. Let's reset it. And we have, so sometimes there's two here, there's two wheels here, but we can just, instead of two wheels here, I'm just going to draw one pulley here like this. And we have a mass here, and we'll call this here M1. And there's string hanging over here, and we will call this here M2, like so. So there's M1, there's M2. Now, this M1 is 120 grams and M2 is 100 grams. So to make our thing match here, or be consistent, we're going to say that M1 is greater than M2, like so. So M1 is greater than M2. All right, and let's see what we got here. Okay, and so if that's the case, then this should rotate in this direction, which means it's going to accelerate in this direction. Therefore, we should call this direction, everything moving in this direction is going to be positive. So we'll go ahead and put positive here. Okay, we'll get rid of this. We'll make this positive, like so, positive. All right, so again, we have no friction. Okay. No friction. So we have no friction. Okay, no friction. Mass of the pulley is 0, and the string has no mass. So string is massless. String is massless. All right, so let's go and take a look at our analysis here. So we have two systems here. So when I do this problem here, I want to focus on this, and then I'm going to focus on that. That's all I'm going to focus on. So let's do system 1 here. So I'm going to assume that all the forces are acting right here. So there is a tension here that's acting in this direction here. Tension is going to act in this direction here. So we'll call this system 1. Okay, so system 1, we'll have here sum of the forces on system 1 is equal to, it's going to be M1A, like so. Okay. And so now, so going down, okay, so here's our free body diagram. We have tension acting upwards, and I have M1G acting downwards. This will be positive and this will be negative. So when I do my sum of the forces here, I'm going to have here M1G, right, minus tension is equal to M1A. Now this tension is the same string, so that's why the T's are the same. So when we go here, that's about as far as I can go. So we're going to go ahead and stop here on this side here. Now over here, I'm going to look at this system here. And I'm going to assume that all the forces are acting on this point right here. So let's do our free body diagram. We have here M2G, right? And going upwards, we have tension, like so. Same string. So this time, this is positive and this is negative. So we're going to do our sum of the forces on system 2 is going to equal M2, was it A here, right? Right. So we have tension minus M2G, M2G is equal to M2A, like so. Okay, it should be M2 here. All right. All right. So we'll go ahead and put a box around this here. Okay, so here's our two boxes. So at this point here, we want to see if the tensions cancel out on the left side. Negative T plus T. The T's are gone. So if I add up everything on the left side, I have M1G minus, so let me go ahead and let's get rid of this here. Okay. Uh, minus M2G, right, is equal to M1A plus M2A, like so. Now here, looks like I can factor out a G, which I will do. And this is M1 minus M2, close parenthesis, equals, let's factor out the A, and I have here M1 plus M2, like so. All right. So here I can either solve for G or I can solve for A. So if I want to solve for A, I want to solve for A here and using my advanced algebra skills, M1 minus M2, like so. And on the bottom here, I have M1 plus M2, like so. So here's how we find acceleration for the Atwood's machine. Okay. All right. Now, where are we at here? Is this part 5? Oh, okay. Here's part 5. The Atwood's machine on an incline. So let's take a look at this and where can we find that? Atwood's machine on an incline. Let me see where that is. So let's hang loose real quick and let me see if I can get that. Atwood's machine, I think it's O physics here. Okay, so Atwood's machine on a incline. Here we go. Okay, click on that. And let's see what comes up here. All right, so here's a inclined plane, Atwood's machine. And I'm going to, let's say there's no friction. So let's take the friction down to 0 and take a look at the boxes. Here's a 20 degrees. Here's M2. This is M1. So right now, M2 is 10 kilograms. M1 is 7.5. Let's see what happens if I click run. So it's going to be rolling up here. Okay, let's reset it. Let's make M2 a little bit less. Let's see what happens now. It's still going up. Okay, so let's make this considerably smaller. Now let's see what happens. Click run. Okay, now it's accelerating down the ramp. Okay, so it's accelerating down the ramp. So let's go ahead and look at acceleration down the ramp. We're going to do a in-class lab, and you're going to determine at what angle are these at equilibrium, and so on and so forth. So we want to take a look at that later on down. We'll do this in a lab. All right, so let's take a look here, and here's our inclined plane like this here, and boy, well, that kind of sucks, but we'll go here. So this has a mass here. Here's our mass here. There's a pulley here. There's a string. It's the same string attached here, and here we have this is we'll call this M1, and we'll call this here M2. So let's see, is there anything else? Or part 7? Yeah, we should be at part 7. Okay. All right. So we have this here. Incline. Okay. All right. So let me see here. Hold on. Before we do this one here, let's look at this case right here. Let me look at this case. Where's the angle at? Can I change the angle? Yeah, I can change the angle. Let's look at this situation here first, okay, before we do the incline. Let's look at this. So let me go ahead and click on run and see it begins to slide like that. Okay, so let's look at this situation first. Okay, hold on. Let me hit pause. All right, sorry about that. So let's take a look at this situation here. And let me go ahead and draw this little sequence here, or a little cliff here, and we'll put a box here. Again, no friction, massless massless string, and the pulley has no mass. So we have a mass here, and we have this hanging like this here. And we'll call this here M1, and I'll call this here M2, like so. All right, so it's going to accelerate in this direction here. There's the acceleration, and we'll call this way going positive. So this direction is positive. Okay, so again, we have two systems. The tension is here. Tension is also here. Okay, so same string, so same tension, no friction. So let's look at this system right here first. Okay, we're going to assume that all the forces are acting on the center of mass right here. So when we do that, then we have sum of the forces on system one. Sum of the forces on system one equals M1A, and the only force acting is tension, is equal to M1A, like so. Over here, we're going to focus on this part right here. All the tension is when we act, all the forces are going to act on this point right here. So we'll put it right here. Free body diagram. We have here M2G, like so. And what's going up is tension, like that. Tension going up. All right, so going down is positive, going up is negative. So when we do our sum of the forces on system 2, it's going to equal M2A, like so. All right, so what we have here is we have here M2G minus tension is equal to M2A, like so. And we'll go ahead and close this box here, and we'll go ahead and close with a box here. Look at the tensions. Do they cancel out? Positive tension minus tension, they cancel out, leaving just M2G on the left side equals M1A plus M2A, like so. So if I want to solve for acceleration here, I factor out the A, and then I can divide by M1 plus M2. So here's M2G divided by, here we have M1 plus M2. All right, so here's the acceleration here. Now let's extend this back to this situation here. So let's reset this, and let's make the angle maybe like right there. Maybe like right here, 14 degrees. Let's go ahead and click on run, and let's see what happens. Oh, we wanted to come down the hill. Hold on, my bad. Let's make it kind of steep like that. 35, yeah, there we go. Let's hit reset and hit run. There we go. See, now it's going down the incline. All right, so this is going to rotate in this direction like this. So this will be the acceleration down the ramp, and we'll call this positive. Now here, here's tension here, and we have tension here. Okay, so now the only force acting and causing it to go down the ramp is the parallel force. Okay, this is from our inclined planes last week. So I'm going to do sum of the forces, right? Is equal to M1A, like so. So positive is going down the ramp, tension is negative. So we're going to have here mg sine of theta, like so, minus tension is equal to M1A, like that. And over here, we're going to look at this system right here. We're going to assume all the forces are acting right here. I'll do my free body diagram. So over here, our free body diagram should have been tension in this direction and the parallel force in this direction here. And we do have the normal force right here. There's a normal force acting there. And we do have mg acting downwards. Okay. All right. Now over here, if we wanted to, we could have done normal force acting upward, and we could also had mg acting this way. But not necessary in this case, but we could have. All right. So back over here, I have tension going up, and we have M2 going down like so. All right, so I'm going to do my sum of the forces in the on system 2 is going to equal, now which way is positive? This is positive going upwards, right? So M2G, okay? So tension is positive, M2 is negative going down. So here I have tension minus M2G is equal to M2A. And this should be A here. Damn it. M2A. There we go. All right, so it should be A here. Okay, so so we'll go ahead and put this in a box here, and we have this way over here also in a box like so. All right, so if I look at do the T's cancel out? Negative T, positive T, they cancel out, so we're good to go. So on the left side of the equation, I have mg sine of theta right here minus m2g, right, is equal to, here's m1a plus m2a. All right, so to solve for acceleration, we have acceleration is going to equal, here's it looks like the g's can cancel out or factor out. So we have here, should be m1 sine of theta, like that, minus m2 divided by m1 plus m2. All right, and that's how we find the acceleration of the inclined plane. Okay, and we'll have some simulations where we have to use this. Finally, we're coming down to a table with 2 pulleys and 3 masses. So let's take a look at this situation here and see what it looks like. Here's our table. It says here 2 pulleys. So we're going to put a pulley here. I'm going to put a pulley here as well. And 3 masses. So I'm going to put a block right here. And maybe we'll call it M3. And it's going to be attached to a string here. And we'll call this here maybe M1. Okay. And there's a block here, which we will call M2. All right. So, and no friction. So we have no friction. Okay, no friction again. Okay, no friction. Okay, so here we're going to say that M1 is going to be greater than M2. So if that's the case, it's going to move in this direction here. It's going to move in this direction. So we'll take this to be positive. This is positive. So now there's two different strings here. Strings are different. This will be T1 and this here will be T2. So there's 2 different strings here. Okay. All right. No friction. So let's take a look at our systems here. And let's go ahead and use red here to kind of get the color. So this will be system 1. Here's system 2. And we'll call this here system 3. Okay. All right. So let's look at system 1 here. So system 1 is we're going to assume all the forces are acting right here. So our free body diagram is going to have T1 acting upwards, and we're going to have here M1G acting downwards. So sum of the forces on system 1 is equal to M1A, like so. Okay, so now going down is positive, going up is negative in this scenario. So we're going to have here M1G minus T1 is equal to M1A. All right, so that's for system 1 here. Look at system 2 here. We're going to assume all the forces are acting right here. So we have tension going up, and no, we'll call it T2 going up, and we have M2G acting downwards. Since it's going in this direction, this will be positive, this will be negative. So we're going to go here, sum of the forces is equal to M2A, like so. So here I have T2 minus M2G is equal to M2A. And we'll go ahead and just kind of pause right here for a second. All right, so we have this and we have this over here. Now, the center part, system 3. Okay, this is some of the forces on 2. So here, system 3 here, we're going to assume that all the forces are acting on here. Now, again, we could do the normal force acting in this direction and mg acting this way. However, we're only concerned about is the horizontal movement here. So positive is this direction, negative is that direction. So we're going to go here, sum of the forces on system 3 is now equal to M3A. Okay, so we have here T1 minus T2, right, equals M3A. All right, so we'll put a box around this. And just like before, here's our equation. Let's look at the left side and see if all the tensions cancel out. Negative T1, positive T1. Negative T2, positive T2. So the left side, all the T's cancel out. Only thing left really is just M1G, right, minus M2G, like so. All right, equals, sum up M1A, M3A, M2A. And we'll factor out the A. So we have here M1 plus M2 plus M3. All right, so to solve for the acceleration, there's the acceleration. It's going to equal, and we're going to factor out the g here. And we have here m1 minus m2 divided by m1 plus m2 plus m3. All right, so there's our acceleration. So this will conclude our discussion of pulleys and tension without friction.